Hey everybody, you're looking right now inside my toaster oven. See those glowing hot heating elements? That's light emission right there. That's caused by atoms that are excited and giving off photons, and we're going to talk about why that is right after I have a date with this taco. Well, hey everybody, hey, Mike here. Boy, that was a good taco. I got 3 cases of them after I went on Craigslist under free stuff, and there was a truck driver who was overshipped and had to get rid of cases and cases. I went and got 3 cases of those tacos for free. Anyhow, good to be here. You can put your calculator away today. It's more or less me telling you stories about how light is produced and sort of the mechanism of that. So let's just go ahead and take what your eyeball sees. You go, don't do this actually, but if you look at sunlight, don't do it directly because in the staring contest, the sun always wins. You'll say that's white light. And for example, this light that's shining on this piece of paper, white light. Now you got to be careful. Your eye, when it sees all of the wavelengths in the rainbow, those mix together to make white. So white is not a color. White is the presence of all colors. And black is the presence of no light. So that's what your eyeball sees the mixture. And if we were to go and take something that was excited, there's a lot of elements in the sun, you see a lot of different wavelengths and it appears as white. But if you take hydrogen gas, which is a very pure substance, you would find out that you could heat this up in a thing called a gas discharge tube. So certainly you would take all of the oxygen out of here so it doesn't undergo combustion. There's a little tube in here, crank it up with enough voltage, you would get some light emission, and your eye would see purple. Now why is that? Well, let's go ahead and say, what if we were to view each through a mechanism, a gizmo called a prism, which is nothing more than a triangular piece of glass that would sort of differentiate the different wavelengths. So what happens is light all kind of goes the same speed and the same angle if it's going through air, but if you pass it through glass, it will slow down and the different wavelengths slow down differently. So if you take sunlight, you shine it through a prism, it will, all the different wavelengths will reflect or will bend and project at a different angle, and you'll see a rainbow. This, of course, happens with dispersed water droplets in the air. They'll refract light in different angles, and that's why you see a rainbow. Not to mention if you take a gizmo called a diffraction grating, where if you got just very, very narrowly etched slits like on a DVD or a CD, and you hit that with white light, all the different wavelengths will bounce off at different angles. And so there's a bunch of different ways that you can accomplish this, but here's what happens. If you go and take white light, you will get what we call a continuous spectrum. You'll see a full and uninterrupted rainbow of Roy G. Biv, the components of the visible spectrum. But if you take that purple light that comes from hydrogen, you only see select wavelengths called a line spectrum. And you don't have to really know this yet, but it turns out you will see 4 different wavelengths. And these could be measured with a gizmo called a spectrometer or a spectroscope. And you'll see something around 600 some nanometers, 490 nanometers, 452 nanometers, and 408 or something like that. And actually it's pretty hard to see this one. You'll see 2 violet lights, lines, and you'll see a green and a red. Why? Well, before we talk about the why, we have to talk about how light is even formed in the first place. Then we'll come back to this. All right? So here is how light is formed. You have in an atom that's not been interrupted by anything, just kind of sitting, hanging out in space. You don't do anything like heat it up or give it energy with voltage or electricity. The electron doesn't fly off because there's Coulombic attraction between it and the positively charged nucleus. So the electron is in an orbit. We could think of it like a moon that's orbiting a planet. That's cool for now. Turns out not all these orbits are circular in nature, but nonetheless, we call this resting state the ground state. And the electron doesn't fly off because of these Coulombic forces. Now, just like my toaster oven, if I went and take atoms and I give them a lot of energy, heck, a blacksmith would be able to discover this. You know that iron would start to glow, and that's because you are taking that extra energy that you put in. That energy is being used to push the electron outward into a further out orbit, and that is called promotion. Okay? And so you could think of it like, what if I was just taking a weight around a string and I was, just swirling it around with my arm, but then I put more energy in, I could make it circle at a much larger radius. Now, that promotion doesn't last forever. Just if like we were going to jump up in the air, we would be reattracted by gravity. Those Coulombic forces take hold once the energy dissipates, and it doesn't take long at all, on the order of femtoseconds, and the electron comes back down. We call that relaxation, but where'd all the extra energy go? That's exothermic. It comes off as either heat or photons. So you have emission giving off photons. Now, this is where in the late 1800s, science got stood on its head, because all you need is a prism to disprove conventional physics. What is conventional physics? Conventional physics would say that due to this particular mechanism, if it was just like regular physics, it would be like this pen. I could take this pen and give it more energy, and I could let it go, and it could go from anywhere to anywhere. I could make it so that it would, I could take it up higher. I could not make it drop on the table. I could drop it on the floor. I need that pen. There's infinite possibilities. That would mean that the electron can go to anywhere and from anywhere, and so when this promotion relaxation happens, you would get, for everything, a continuous spectrum, because there's infinite possibilities. Now, it turns out that's not the case. What's the case is we got a line spectrum. There's only some possibilities, and that's because of the existence of quantum levels. That is, that the places the electron can go to and from are limited by quantum levels. Just like if we were to go inside a building, we can only go on certain stories. It's kind of like that. There's only certain finite places an electron can go. So those are called quantum levels. That's why when you look at the light given off by elements, you have, if they're in their pure state, you have only discrete wavelengths possible. And then you could say, well, hey, isn't the sun composed of elements? Yeah, but the sun's a mixture of a whole bunch of elements. If you were to separate all those elements, you would get a line spectrum for each one. As a matter of fact, if you look at sunlight, you would find that that rainbow really actually is tiny, tiny discrete lines, just lots and lots of mixtures of them, so it appears white. So if there was enough discrete lines, you would see white because your eye would just blend them all together. The reason we see purple with hydrogen is because red and green and violet mix together to make purple. So, what about these quantum levels? Well, we're going to do a lot of math stuff next time with them, but I'll just kind of talk about them very generally here. And I'm going to continue to talk about them as if they're spheres. That's going to be just fine. So, all right, you've got different levels called quantum levels, and they are given the number n equals 1, 2, 3, 4, 5. out to wherever. And all atoms have these quantum levels. I want to repeat that. All atoms have these quantum levels. They might be spaced differently. They might be populated by different numbers of electrons, but they all have this template. And I want you to really understand that you don't have to know why. You know, this is just is what it is. And I often tell my students, you know, we don't know why that happens. And they could say, well, it's gravity. Gravity, and then the Earth has mass, and this pen has mass. And I'll say, why? And then they'll say, because 9.8 meters per second, it's gonna attract each other. And then I'll say, why? And then you run out of whys. You can't answer. So it just is. Okay, there's quantum numbers, there's quantum levels. The electrons can go in there. They can go between, back and forth. And so here we'll get into the rules. First of all, we call this principal quantum number, n equals 1, 2, 3. Each can hold a different number of electrons. Getting into that next few times. As a matter of fact, that'll be several talks from now. So basically an electron's got to be in a quantum level. It can't be in between. It's got to be in 1, 2, 3, 4. It can be in any one, which means if you put enough energy into it, you can push the electron. Now let's be an electron. Let's say we're hydrogen. Where are you going to want to go? You're going to want to go as close to the nucleus as you can. And that's why we call that the ground state. But if we put enough energy in, you could push it up to n equals 2. If you put more energy in, you could push it up to n equals 3, 4, 5. It depends on how much energy that particular electron has acquired at any time, and there's a lot of probability to that. And in a population of atoms, there's lots and lots of atoms. And if you take Avogadro's numbers of atoms, there's a lot of atoms doing different stuff. Some are lucky enough to get enough energy and some aren't. But the bottom line is if an electron gets enough energy, it could be promoted. This electron could be promoted to 2, 3, 4, 5, depending on how much energy it gets. And it can go from any level to any level. And so, for example, let's say this electron were to get enough energy to go up to, you know, n equals 4. Well, now it stays up there. It could relax to n equals 3. It could relax to n equals 2, n equals 1. It's pure probability. Now, what I can tell you is there's a lot more probability that an electron can get from 1 to 2 than from 1 to 5. See, so if you heat up a bunch of atoms or you give them a lot of energy, there's diminishing returns of probability that an electron can get to n equals 5. It's like if I said, okay, everybody, let's go climb a mountain. And then, you know, we got 2 hours. Go as far as you can. There'd be a lot of people that wouldn't maybe be able to get to 5,000 feet. And there'd be a lot more people that could get to 1,000 feet. It's just like that with electrons and atoms. One little interesting thing is that as you go outward from the nucleus, don't have to understand why, but just is, they become closer in energy. So you see how 5 is closer to 4 than 4 is to 3. So actually, if let's say this electron were to go and jump down from n equals 4 to n equals 3, well, that wouldn't be as much energy if the next one it went from 4 to 2. As a matter of fact, this jump from 4 to 3 you can't even see because it's in the infrared. But the electron jumping from 3 to 2, you can see it's the red line in the line spectrum of hydrogen. And so that is sort of, you know, just using hydrogen. If I had sodium, there'd be 11 electrons. And they could all be doing different stuff. So you see it gets quite complex. But the thing is that as the n levels go further out, they do become closer in energy, but they can also hold more electrons. So nature has some sort of weird averaging thing that goes on here. All right, so we got this framework for every element in the periodic table, every atom that's possible in the universe. So why don't we start simple? Let's just say 1 electron. And this is what Niels Bohr and associates did in the late 1800s. All you need is a gizmo like a prism, You could calibrate something with, you know, figure out what angle, or the color, frankly, could tell you the wavelength. But what we have is different possibilities for hydrogen. So just with one electron, it's very simple because you only got one electron doing one thing at one time. And it gets a little messy because if you go and add another electron, now one electron affects the other. So here's what happens. Let's say we heat hydrogen and we keep track of where all the electrons go to and from, and then we look at the light that comes off. We have gizmos that can measure wavelength very accurately called spectroscopes, and basically at the angle that a diffraction grating bounces the light off, you can calibrate that with something of a known wavelength, like my green laser pointer or something like that, and then you could say, well, that angle is 552 nanometers. And then you can go and look at something brand new and determine what it is. As a matter of fact, the line spectrum of every element is its own fingerprint. If you were to take something, an unknown, and you say, hey, it burns purple, you could say that's probably hydrogen. Or if you could say, hey, it burns violet, that's probably potassium, or heat it up and it becomes violet. If you say, hey, it's brick red, that's calcium. Green, it's copper. And so when you look at fireworks, you're seeing the line spectrum of different pure elements. But now we're going to stick to hydrogen. Those four wavelengths happen to be a series where they're organized based upon where they end up. So they have the Lyman series is something where all the electrons end up at n equals 1. Now, because of the quantum levels getting closer together as you get further out from the nucleus, even n equals 2 to 1, even though it's one quantum level jump down, you can't see it. It's invisible because it's in the ultraviolet range. Remember our little thing that we were talking about last time with the visible range being lower in energy than UV. And so it happens to be that all these jumps downward are happening at a time. But out of these, I don't know how many that is. What is that? That's 5 relaxations, 9, 12, 15 relaxations. Out of all those, you can only see 4. And as a matter of fact, you really can't even see this one 6 to 2 well because it's violet and your eye isn't good at seeing violet. And the probability of an electron getting to n equals 6 is very low. So you can see a red line. If you look at hydrogen through a spectroscope, you see a green one, and then you see 2 violet ones. And then that's it. Because if you get up to n equals 7, now you're getting into the UV and you can't see it. All of these other series called Paschen series, this is something down to 3. 6 to 3, 5 to 3, 4 to 3. They're all happening, but they're too low in energy to see because they're lower energy than or higher wavelength than the visible range. And so this proved the existence of quantum levels for hydrogen because of the fact that there was only certain ones. And you can measure these. You can't do it with your eyeball, but there's detectors that can detect UV and IR and even radio waves up here. If it goes past IR, probably the 6 to 5 might even be on the order of way at the end of infrared. And so these are the series, and they have names named after people. The Balmer series of hydrogen is anything quantum level down to quantum level number 2. What we're going to talk about next time is that Bohr and company cracked the code for all this. This is the equation that they figured out. It's actually what you call an inverse square rule. A lot of things in science are an inverse square rule, which means that the energy is proportional to 1 over the n squared. I believe that something like earthquake damage is an inverse square rule. That means if you double the distance, you cut the amount of energy into 1/4, 1 over 2 squared. And so what we got here is this is the energy of the photon that's given off, or the energy of the electron that was lost. So this is where we have energy going up here. So this could be this energy change here. Let's take 3 to 2. That's the change in energy, which is converted to a photon. And so the energy loss of the atom and the energy of the photon is the same, is a constant in joules, and divided by 1 over the n squared final. This is the final. This is where the electron ended up, minus 1 over 1 squared initial. So 3 to 2 was our example. This would be 3. Excuse me. This would be 2. This would be 3. So it would be, in this term, it would be 1 divided by 2 squared, which would be 1/4. 1 divided by 3 squared, which is 1/9, and then times that. And this would be the energy of the photon, which, as you know from last time, could be converted to the frequency, which could be converted to the wavelength. And those energies, so what you really got going on is you look at hydrogen with a spectroscope, you measure all the wavelengths, you back calculate the energy, you figure out what the ends were. If it's hydrogen and you saw it, you know that n final is 2. And so this is what proves the existence of quantum levels. Start with a simple model, like something that only has 1 electron. And so next time, your calculator might feel lonely, but bring it out, because we are going to prove the existence of that equation by plugging in first a bunch of n's and calculating the wavelength, and then having a wavelength and calculating the n's, which is what Bohr and company did to prove their equation. Folks, it's getting a little Star Trek-y here. I know that, here we are to understanding stuff like heat and stuff that you can, I can understand exothermic, endothermic, and this gets a little weird. Electrons are weird. They don't behave like regular matter. And that's this whole other field called quantum physics. And we won't go into it too deeply, but we'll go into it enough, because electrons get a little weird, and you'll see that when we talk about how bonding works, because it's all about the electrons. Good talk, folks. I think I'm going to go have another taco. Take care of yourselves. We'll see you next time. Later.